All right, so check this out. Last time, or previously, we were looking at the fundamental theorem of calculus, which states we've got two principles, or two parts of the fundamental theorem of calculus. First part is when we have a function that's continuous on a closed interval a, b. First, the derivative of the integral is equal to the integrand, the value of the function inside the integral, evaluated at that upper limit. A reminder, chain rule for that. The second part of the fundamental theorem of calculus is called the integral evaluation theorem. So that if we have what we're going to call a definite integral, so definite, definite, like this is a number. When we have a definite integral, we've got the lower bound, the upper bound. It's equal to the antiderivative of our integrand, the function inside, evaluated at the upper bound. Subtract the antiderivative evaluated at the lower bound, where, of course, as I just kind of inferred, the derivative of big F of x is our integrand, little f of x. So the fundamental theorem of calculus connects the derivatives and integrals as inverses, inverse functions, and the integral can be evaluated by determining an appropriate antiderivative. Now, using this notion of antiderivatives, we're going to develop a notation. We're going to have what we call an indefinite integral. The indefinite integral is, notice the difference, we have no bounds. So we are not evaluating for any specific number. So this would be still the integral of f of x dx would give us our antiderivative. We're actually missing a little bit here. So our indefinite integral, we looked at antiderivatives before. It is just fancy notation saying find the antiderivative, find the general function. Now, what we did before was I may have given you find the general antiderivative of x squared. Well, we would have gone through and okay, that's 1/3 x cubed because the derivative of 1/3 x cubed is that x squared. But we also have this constant term. Remember this plus c, a constant, because it can be any of that family of functions. The derivative, when we have that constant, remember the derivative of a constant is just 0. So new stuff, or just changing our definition a little bit. The definite integral requires a lower bound and an upper bound. That gives us a number, a numerical value. It equals some quantity. An indefinite integral has no bounds, no lower upper bounds. This gives us a function, or specifically a family of functions, where they all differ based upon that constant c. So a definite integral definitely has those bounds. Indefinite integral can be any function, because we've got that family, not any function, but we've got that constant included there. So let's check it out. Now, here's a table of common indefinite integrals. Don't memorize these. It's just the reverse of our derivative rules. We know our derivative rules. You've got to know the derivative rules. So we know going forwards, we know going backwards, thinking about that hierarchy. Kind of stepping down from a function gives us our derivative, stepping up is the antiderivative, is the integral. So just to comment on a few things, the integral of a constant multiple, we can take that constant multiple outside of our integral. Sum of integrand functions is equal to the sum of integrals. We can take each one separately. Integral of a constant would give us kx, everything plus our c. We've got the reverse of the power rule where we add 1, divide. The antiderivative of the natural log, of 1 over x gets us the natural log, and we discussed previously about why we need the absolute value, thinking about the domain of that function, negative infinity to 0, along with 0 to infinity, so that absolute value makes certain that we have the same intervals. E to the x gives us e to the x. Any base function, b to the x, gives us b to the x over natural log of b. Now, when we are anti-differentiating, we can always take the derivative to check ourselves. We've got sines, cosines, and the rest. Follow along. It is the same, just the reverse of our derivative rules. Always remember that constant plus c when finding that general antiderivative. So let's try out a few examples. And the general antiderivative of integral of 10x to the fourth plus secant squared x. Well, I can break this apart if I need to. This is the integral of 10x to the fourth dx plus the integral of secant squared x dx. Now, I can think about it separately if I need to, but I don't find the need to do that. So here we've got the power rule. This is going to be 2x to the fifth. Checking that, 5 times 2 would give us 10, subtract 1, all right. Secant squared, the antiderivative of that is tangent of x plus our constant c. One integral, I have one constant. Let's check out the next one. Integral of cosine over sine squared dx. I'm going to rewrite this. This is going to be 1 over sine x multiplied by cosine x over sine x dx. I do that because I need a little bit of trig manipulation to make things a little bit more pretty to work with. This is the integral of cosecant x. That's cotangent of x dx. And we recognize that as being the derivative of cosecant x plus c. Ooh, but if we check this, the derivative is negative cosecant cotangent. So here's the balance. Make certain that we check, we find those coefficients, or in this case, the negative. Carry on. Now here we have a definite integral. We have bounds. We're going to first find the antiderivative and then evaluate. So I'm looking at each piece individually. This will give us 1/4. X to the fourth, subtract. That's going to give us 3x squared. And we're going to evaluate. Remember, I use that notation. Evaluate. I use the solid line saying I'm going to evaluate from 0 to 3. So this is going to give us 1/4. That's 3 to the fourth minus 3, 3 squared. Subtract 1/4, 0 to the fourth minus 3, 0 squared. Of course, we recognize that that's just 0. And so this gives us negative 27/4. Check that work. Carrying on. So find the definite integral of this. So I'm looking at each piece individually. That first 2x cubed is going to give us x to the fourth over 2. Is that correct? So 4 times 1/2 gets us 2. Subtract 1. Yep, okay. We've got minus 3x squared plus, 3. Well, that 3 is just a constant. I look at this as 1 over x squared plus 1. That's arctan. So it's 3 arctan x. All of that evaluated from 0 to 2. So that's going to give us 2 to the fourth over 2. Subtract 3, 2 squared, plus 3 arctan of 2. Subtract. We've got 0 to the fourth over 2. Subtract 3 times 0 squared, plus 3 times arctan of 0. So this gets us 8. Oops, why did I switch that? 8. Subtract 12, plus 3 arctan of 2. Subtract. That's 0. That's 0. And arctan of 0 is a tangent of what angle gives us 0. That's 0. So that whole thing is just 0. That gives us with negative 4 plus 3 arctan of 2. I don't know that value. That's not off our unit circle. That's not something nice. We can plop that in a calculator and get a decimal, or there it is. It's done. Example number 5. Evaluate, once again, a definite integral. Ooh, yikes. We've got this quotient. Here's what I'm going to do. I'm going to distribute that t squared to every single term. So I'm going to rewrite this. Integral from 1 to 9. Well, t squared, 2t squared over t squared is just going to be 2 plus t squared root t. That's going to be t to the 1/2 is remaining minus 1 over t squared. That's t to the negative 2. I'm rewriting that because now I can easily apply the power rule. So this is going to give us 2t, because that's just a constant, plus 2/3 t to the 3/2. So check that. 3/2 multiplied by 2/3 gives us 1. Subtract 1 gives us 1/2. And then plus t to the negative 1. Yeah, evaluated from 1 to 9. So this is going to be 2 times 9 plus 2/3 times 9 to the 3/2 plus 9 to the negative 1. That is going to be subtracting. We've got 2 times 1 plus 2/3 times 1 to the 3/2 plus 1 to the negative 1. So that is, let's just simplify some things. It's 18 plus, that is 9 to the 1/2 is 3. 3 cubed is 27. That's going to be 18 plus 1/9. All right, so that's 36 plus a 9th. That's 324 over 9. Subtract. This is 2 plus 2/3 plus 1. That's 2 plus 2/3 plus 1 gets us 11/3. So that is subtract 33/9. Gives us 291/9, which is also 97 over 3. Check that. Follow along. Now, some applications. The fundamental theorem of calculus part 2 says for any continuous function f on that continuous on that closed interval. I suppose I don't need that. For any function f on a continuous interval ab, our integral evaluation theorem states that as the antiderivative of the upper bound subtract the antiderivative of the lower bound. What this means is we saw this is the area under the curve, area under a specific curve, but that's also the net change. And so thinking kind of when we had those negative areas, when it's below the x-axis, it's the net change, the net area. We call this the net change theorem. And this really applies to physics, biology, when we're comparing how something is changing over time. You might gain something, you might lose something. So if this is velocity, Well, this would be the position at time B, subtract the position at time A. Well, position at one time subtract, that's your change in position or your displacement. In terms of population, it might be the change in population. So a population of bacteria grows at this rate, where P prime of T is measured in cells per hour. At time equals 1, there are 100 cells counted in a petri dish. If left to reproduce without limitations, what is the expected number of cells 1 day later? Well, that's T equals 1 hour. 1 day later, that would be 24 hours later, giving us 25 hours. So we've got this rate of reproduction, or the rate of change of our population with respect to time, going from 1 to 25. So what this is when we're looking at our rate of reproduction, so what's the net change from the population at 1 to 25 hours, or 1 day later? So this is going to be the integral from 1 to 25 of 5e to the 0.02 t dt. Now we know that, that's going to be e to the 0.02 t. We're going to evaluate from 1 to 25, but checking our derivative of e to something is e to something. Ooh, chain rule, 0.02 multiplied by what gets us 5. So that's going to be 0.02, that's 1 over 50, so 1/50th of something. Well, 50 times 5 is 250, so that's going to be 250 e to the 0.02 t. And if we plug that in, we can plop that into the calculator. We get about 157 total cells, or change in cells, total change. But remember, we started off with 100 at the initial, t equals 1. So we've got a total of 257 total cells 1 day later. Another time when we can see this is distance versus displacement. So a particle moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6. Now that's in meters per second. I want the displacement of the particle. So that's the net change. The particle during the time period from 1 to 4. So part A, we're going to have the integral 1 to 4 of t squared minus t minus 6 dt. And so we can find the antiderivative. That gets us 1/3 t cubed minus 1/2 t squared minus 6t. It's going to be evaluated from 1 to 4. So this, we're going to plug in 4. So we've got 4 cubed over 3 minus 4 squared over 2 minus 6 times 4. We're subtracting 1/3 minus 1/2 minus 6. That's when I plugged in 1 everywhere. Now that gives us, we can plop that in a calculator or crunch that out, that gets us -9 halves. So the units are in meters. What that means is from our starting position to our end, we are now 4.5 meters left, negative, of our start. But what's our total distance? Now, if we get out of bed in the morning and you walk to school, you walk around the building, and then you walk back to school, you've gone a certain distance. But then at the end of the day, you're back home. Your net change, your displacement, getting back into bed is 0. But you've done a whole lot of distance. If you are running around a track, you want to keep track of how many times you've gone around, how many laps you've done. If you start and stop at the same position, well, you don't want to say that you ran 0 miles after you ran 30 laps around the track. It's what's your total distance. Now, so here, if we think about our velocity function, we've got t squared minus t minus 6. Well, this factors into t minus 3 and then t plus 2. So if we look at like a sign chart, -2, 3, we're positive to the left of -2. We're negative between -2 and 3, and then we're positive after that. Now, so our velocity, so we're increasing, we're decreasing, then we're increasing. So we're moving to the left, we're moving to the right. We care about the total distance. Now we're going from 1 to 4. So that means from time equals 1 to 4, 1 to 3, we're actually moving to the left, but we want to count that distance. So what we're going to do, this 2 ways. We're going to take the integral from 1 to 3, just 1 to 3, that left, t squared minus t minus 6 dt. We're going to make that possible. I'm going to take the absolute value of it because I want the distance, not the displacement. I'm going to add to that the integral from 3 to 4 of t squared minus t minus 6 dt. Now this gets us, if we plop that in, evaluate that. That's negative 22 over 3. That's 22 thirds, or 7.3 meters to the left. So I actually want that to be 22 over 3. Plus, this one comes up to be 17 sixths. So we're going to add those two. So we've got our distance to the left. Our distance to the right gets us a total of 61 sixths, or 10.16 meters traveled. That's our total distance versus our displacement. If we took this as negative plus that, we get back to our negative 9/2 meters.